Hi, my name is Tom Lever. I've recorded this video to offer you a guide to getting started using Google Colaboratory to draw bounding boxes around objects in images or videos. More technically, I'm offering you a guide to getting started using a Python 3 kernel on a Linux virtual machine hosted by a Google server to compile AlexeyAB's deep learning framework called darknet, and using the kernel to run a compiled executable file, also called darknet. In running darknet, the kernel will forward propagate an image or video through a YOLOv3 convolutional neural network, use the resulting prediction matrices to hopefully draw bounding boxes around objects in the image or video frames, and archive the image or video. The neural network may be trained on the COCO dataset, the Pascal VOC 2007 and 2012 datasets, or a custom dataset. Let's begin. Jupyter Notebook is a web browser-based application installed on my Windows 10 PC that allows me to create documents that contain live code, equations, visualizations, and narrative text. The documents that I create using Jupyter Notebook are also called Jupyter Notebooks. While using Jupyter Notebook, I can employ the Python 3 kernel to execute Python code, execute command prompt commands, access local files, access local hardware like my webcam, and access folders and files on remote servers. Google Colaboratory is a Jupyter-like application installed on a Linux virtual machine hosted by a Google server. The documents that I create using Google Colaboratory are also Jupyter Notebooks. While using Google Colaboratory, I can employ the Python 3 kernel to execute Python code, execute Linux terminal commands, access files local to my virtual machine, access information received by the browser on my local Windows 10 PC, like requested webcam images, and to access folders and files on remote servers. To create a Jupyter Notebook using Google Colaboratory, I open Google Chrome, enter https://drive.google.com, press enter, scroll down a little bit, left click, go to Google Drive, enter my email address, press enter, enter my password, press enter, press save, right click within the window to all the folders and files in the root folder of my Google Drive, left click new folder, enter darknet, press enter, double left click darknet, right click within the window to all the folders and files in my darknet folder, place my mouse cursor over more, left click Google Colaboratory, press no thanks, left click file, left click rename, enter YOLO version 3 detecting.ipy notebook, and press enter. To set up our YOLO version 3 detecting Jupyter Notebook, I left click edit, left click notebook settings, left click the down pointing triangle below hardware accelerator, left click GPU, and left click save. I left click the right pointing chevron left of the first code cell, and left click files. When I employ the Python 3 kernel in accessing files, the kernel assumes by default that the files are stored in the root/content directory, where root is the root directory of my virtual machine. To navigate to the root directory of my virtual machine, type $cd ... in the first code cell and execute the command by left-clicking the play button or pressing and holding Shift and pressing Enter. To return to the root/content directory, execute the command $cd content. To view the contents of the root/content directory, execute the command !ls. To copy darknet, AlexeyAB's deep learning framework, to the root/content directory, I execute the command !git clone https://github.com/AlexeyAB/darknet. Now I want to prepare to compile, likely, darknet solution in the root darknet build darknet directory into the executable file darknet in the root content darknet directory. To do this, I navigate to the root content darknet directory by executing the command $cd darknet. I'm now in the root content darknet directory. I modify AlexeyAB's makefile in this directory to configure the darknet binary to perform matrix computations using Google's graphical processing units, use NVIDIA Corporation's CUDA deep neural network library, and use the OpenCV team's OpenCV library. I modify AlexeyAB's makefile by executing the commands !stream editor in place single quote substitute first argument to replace second argument what that replaces with / makefile. Similarly, I'm still in the root content darknet directory. To compile darknet solution into the darknet binary, I execute this simple command !make. To use the darknet executable file to place labeled bounding boxes around the objects in this image, dog.jpg, I will eventually execute the following command. Exclamation point, which tells the Python 3 kernel that the command is a command to be executed on the Linux kernel on my virtual machine. A reference to the darknet binary, a reference to the detector function, a reference to the test command as opposed to the train command, a reference to a data file, a reference to a configuration file, a reference to a weights file, and a reference to the image. I will copy this command, less the exclamation point. You'll see why I copied the command in a little bit. Before running my darknet executable file, I want to prepare data files, like COCO.data. Each data file will provide darknet with information on the number of classes of objects I have identified in the images in my training dataset, the location of a text file listing of the paths to images in my training dataset, the location of a text file listing of the paths to images in my test dataset, the location of a text file listing of the names of classes of objects, and the location of a folder in which to save a weights file that the darknet binary will use to initialize the values in each cell in each filter in the YOLOv3 convolutional neural network. Joseph Chet Redmond is the creator of the original darknet deep learning framework. AlexeyAB offers an optimized version of Redmond's framework. Instructions on how to use Redmond's and AlexeyAB's frameworks are available on Redmond's YOLOv3 webpage. To navigate to Redmond's YOLOv3 webpage, open a new tab in Chrome, type https://pjready.com. Press enter, left-click Darknet, scroll down a little bit, and left-click YOLO Real-Time Object Detection. The data file corresponding to Joseph Chet Redmond's first presented command to locate objects within an image, which you've seen before, and which corresponds to locating objects associated with the COCO dataset, is COCO.data. One version of COCO.data is located on our virtual machine in root, content, darknet, configuration, COCO.data. Execute the command, exclamation point, head 6, reference to COCO.data, to display the first 6 lines of code in COCO.data. I want to revise COCO.data to reference a text file listing on my virtual machine of paths to training images, a text file listing on my virtual machine of paths to test images, a text file listing on my virtual machine of the names of classes of objects, and a folder on my virtual machine in which to save a weights file. I want COCO data to look like this. To get COCO.data to reference files and a folder on my virtual machine, I execute the commands, exclamation point, stream editor, in place, substitute, for, substitute with, end pipe character, reference to COCO.data. Similarly, executing. Here, because I use forward slashes in the paths that I wanted to replace and wanted to replace with, and chose to use pipe characters to delineate, substitute what to replace with, I need to be consistent in my use of pipe characters and forward slashes. Rerunning. It seemed to work. I will check that my version of COCO.data references files in a folder on my virtual machine by executing the command !head 6 reference to COCO.data. Checking. It seems that my version of COCO.data corresponds to the file structure on my virtual machine. Cleaning up, I will remove my reference to the command I will eventually use to have the darknet binary place labeled bounding boxes around objects in an image. And will remove my reference to what I wanted my version of COCO.data to look like. The data file corresponding to locating objects associated with the Pascal VOC 2007 and 2012 datasets is voc.data. One version of voc.data is located on our virtual machine in root content darknet configuration voc.data. Execute the command !head 6 reference to voc.data to display the first 6 lines of voc.data. I want to revise voc.data to reference a text file listing on my virtual machine of paths to training images, a text file listing on my virtual machine of paths to test images, a text file listing on my virtual machine of the names of classes of objects, and a folder on my virtual machine in which to save a weights file. I want voc.data to look like this. To get voc.data to reference files in a folder on my virtual machine, I execute the commands !stream editor in place, substitute for substitute with end pipe character reference to voc.data. Similarly, executing. Here, I forgot an end pipe command. I will check that my version of voc.data references files in a folder on my virtual machine by executing the command !head 6 reference to voc.data. It seems that this version of voc.data references my virtual machine's file structure. Cleaning up, I will remove my reference to what I wanted my version of voc.data to look like. To create a data file corresponding to locating objects associated with my own dataset of 100 images of oak leaves from various species in Quercus, the genus of oak trees. On my Windows 10 PC, I minimize my Jupyter notebook, press and hold Shift, right-click my desktop, left-click Open PowerShell window here, reposition, and resize my PowerShell window. Right Notepad, press Enter, reposition, and resize my Notepad window. Left-click File, left-click Save As, delete the suggested file name, press the down-pointing chevron right of Save as Type, left-click All Files, enter object.data as file name, and left-click Save. To fill in object.data, I write classes equals 1, because I'm only identifying Quercus images. Train equals the path to the listing of paths to training images. Valid equals the path to the listing of paths to the testing images. Names equals the path to the listing of names of classes of objects associated with YOLO version 3 convolutional neural network trained on my OAK-Leaf dataset. And backup equals backup the path to a folder where darknet will save a weights file that I can use to initialize the values in the cells in the filters in the YOLO version 3 convolutional neural network. I will save object.data by left-clicking File and left-clicking Save. I will return to view our Jupyter notebook, YOLO version 3 detecting. At this point, I'm going to minimize my files outline. To copy object.data from my desktop on my Windows 10 PC into the file root, content, darknet, configurations, object.data, I navigate to my Google Drive's darknet folder. Right-click within the window to all the folders and files in my darknet folder. Left-click Upload Files, left-click Object.data, and left-click Open. I then navigate back to my Jupyter notebook and navigate to the root content directory by using the command $cd ... While in the root content directory, I mount my Google Drive as a virtual drive accessible by my virtual machine by executing the Python code from google.colab import drive.mount content drive. I left-click the URL, left-click my name, scroll down a bit, left-click Allow, left-click the Copy button, navigate back to my Jupyter notebook, right-click in the text box under Enter Your Authorization Code, left-click Paste, press Enter. Left-click Refresh, and close the authentication window. Here is my Google Drive, accessible as a folder/drive on my virtual machine. I'm still in the root content directory. To copy object.data from my Google Drive's darknet folder to the root content darknet configurations object.data directory, I execute the command copy drive my / as an escape character space drive darknet object.data to darknet configuration object.data. I then navigate back to root content darknet by executing the command $cd darknet. I next want to prepare configuration files. Each configuration file will provide darknet with information on how to organize images into batches and subdivisions, also known as mini-batches. When I train darknet's YOLOv3 convolutional neural network, darknet divides my training set into batches with 64 images each, and divides each batch into 16 subdivisions with 4 images each. Darknet then forward propagates each matrix representing a subdivision of images through the YOLOv3 convolutional neural network, captures the losses output by the 82nd, 94th, and 106th layers of the network, averages these losses into a cost, and adjusts each value in each cell in each filter in the network based on the existing cell value, the learning rate, and the value of a function representing the derivative of the cost with respect to each cell value. When I employ darknet to identify objects in an image, darknet divides my set of one image into batches with one image each, and divides each batch into one subdivision with one image. The configuration file corresponding to Joseph Chet Redman's first presented command to locate objects within an image, and corresponding to locating objects associated with the COCO dataset, is YOLOv3.cfg. One version of YOLOv3.cfg is located in root, content, darknet, CFG, YOLOv3.cfg. YOLOv3.cfg does not need to be modified to locate objects. Execute the command !head 7, the path to YOLOv3.cfg, to display the first 7 lines of this file. Note that these 7 lines configure darknet to divide a test set of one image into batches with one image each, and divides each batch into one subdivision with one image. The configuration file corresponding to locating objects associated with Pascal VOC 2007 and 2012 datasets is YOLOv3-voc.cfg. One version of this file is located in root, content, darknet, configuration, YOLOv3-voc.cfg. This file does not need to be modified to locate objects. Execute the command !head 7 reference to YOLOv3-voc.cfg to display the first 7 lines of this file. Note that these 7 lines configure darknet to divide a test set of one image into batches with one image each, and divides each batch into one subdivision with one image. To copy a configuration file corresponding to locating objects associated with my own dataset of 100 images of oak leaves from various species in Quercus, the genus of oak trees, from my Google Drive's darknet folder to the file root, content, darknet, configuration, YOLO version 3-object.configuration, I navigate to the root content directory by executing the command $cd ... Here, I execute the command !copy from drive my/drive darknet YOLO version 3.object.configuration to darknet/configuration/YOLO version 3-object.configuration. I navigate back to root content darknet by executing the command $CD darknet. I next want to prepare weights files. The darknet binary will use each weights file to initialize the values in each cell in each filter in the YOLO version 3 convolutional neural network, when either training the network or forward propagating an image or video frame through the network. The weights file corresponding to Joseph Chet Redman's first presented command to locate objects within an image, and corresponding to locating objects associated with the COCO dataset, is YOLOv3.weights. To download YOLOv3.weights to root, content, darknet, YOLOv3.weights, execute the command !wget http://pjready.com/media/files/YOLOv3.weights. To copy a weights file corresponding to locating objects associated with the Pascal VOC 2007 and 2012 datasets from my Google Drive's darknet folder to a form of the file root content darknet YOLOv3-voc.weights, I navigate to the root content directory by executing the command $cd ... Here, I execute the command !copy drive / my \escape character space drive / darknet / YOLOv3-voc2000.weights to darknet / YOLOv3-voc_2000.weights. The copy was a little slow, but that was because the file size for a typical YOLOv3.weights file is around 235 megabytes. That being said, I was checking over there to the left on whether the drive was properly mounted and available for copying. This particular weights file is output by the darknet binary after using darknet to train a YOLOv3 convolutional neural network by performing 2000 iterations of forward and backward propagation of a batch of images through the network. At this point, I navigate back to root content darknet by executing the command $cd darknet. To copy a weights file corresponding to locating objects associated with my own dataset of 100 images of oak leaves from various species in Quercus, the genus of oak trees, from my Google Drive's darknet folder to a form of the file root content darknet YOLOv3-object.weights, I navigate to the root content directory by executing the command $cd ... Here, I execute the command !copy from drive / my \escape character space drive /darknet /YOLOv3 object underscore 2000 dot waits to darknet YOLOv3 object underscore 2000 dot waits. This particular waits file is output by the darknet binary. After using darknet to train a YOLO version 3 convolutional neural network by performing 2000 iterations of forward and backward propagation of a batch of images through the network. I navigate back to root content darknet by executing the command $cd darknet. I next want to prepare names files. Each names file will provide darknet with a listing of the names of classes of objects that I identified in images when I trained the YOLO version 3 convolutional neural network. The names file corresponding to Joseph Chet Redman's first presented command to locate objects within an image, and corresponding to locating objects associated with the COCO dataset, is COCO.names. One version of COCO.names is located in the root content darknet data directory and is called COCO.names. COCO.names does not need to be modified during either training or detecting. Executing the command !head 5, the path to COCO.names will display the first 5 lines of COCO.names. The names file corresponding to locating objects associated with the Pascal VOC 2007 and 2012 datasets is voc.names. One version of voc.names is located in root content darknet data voc.names. voc.names does not need to be modified during either training or detecting. Execute the command !head 5, the path to voc.names to display the first 5 lines of voc.names. To create a names file corresponding to locating objects associated with my own dataset of 100 images of oak leaves from various species in Quercus, the genus of oak trees, I first close object.data, navigate to my PowerShell window, write Notepad, press Enter, reposition and resize my Notepad window, left-click File, left-click Save As, delete the suggested file name, press the down-pointing chevron right of Save As Type, left-click All Files, enter object.names as the file name, and left-click Save. To fill in object.names, I write the single line Quercus. I will save object.names by left-clicking File and left-clicking Save. I will return to view our Jupyter Notebook YOLOv3 detecting. To copy object.names from my desktop on my Windows 10 PC into the file root content darknet data object.names, I navigate to my Google Drive's darknet folder right-click within the window to all the folders and files in my darknet folder, left-click Upload Files, left-click Object.names, and left-click Open. I then navigate back to my Jupyter notebook and navigate to the root content directory by executing the command $cd ... To copy object.names from my Google Drive's darknet folder to the root content darknet data object.names file, I execute the command $copy from drive/my/escape character space drive/darknet/object.names to darknet/data/object.names. I then navigate back to root content darknet directory by executing the command $cd ... darknet. Now it's time to finally execute our darknet binary in the root content darknet directory. To do so, execute the command $darknet detector, a reference to a function, a reference to the test command as opposed to the train command, a reference to COCO.data, a reference to YOLOv3, our configuration file, a reference to YOLOv3, our weights file, and a reference to our image of a dog, a bicycle, and other objects. Executing. To display the image of the dog and the bicycle, execute the Python code from ipython.display import image predictions.jpg. And here is our image dog.jpg with the dog, the bicycle, and the truck, all labeled with bounding boxes and class names. To use our darknet binary to forward propagate an image of a great blue heron in a natural setting on my PC desktop through a YOLOv3 convolutional neural network trained on the VOC 2000 and 2012 datasets, I navigate to my Google Drive's darknet folder, right-click within the window to all the folders and files in my darknet folder, left-click Upload Files, left-click Great Blue Heron.jpg, and left-click Open. I then navigate back to my Jupyter notebook and copy the image of the great blue heron from my Google Drive's darknet folder to the root content darknet data folder by executing the commands $cd ... copy from drive/my/escape character space drive/darknet/great blue heron.jpg to darknet data great blue heron.jpg. Finally, I execute $cd darknet to return us to the root content darknet folder. I then forward propagate the image of the great blue heron by executing the command !/darknet, a reference to the detector function, a reference to the test command as opposed to the training command, a reference to voc.data, a reference to YOLOv3-voc, our configuration file, a reference to YOLOv3-voc_2000, our weights file, and a reference to the great blue heron image. I'm reading this error about not being able to open the file YOLOv3-voc_2000.weights in the configuration folder of our darknet folder. Checking this configuration folder, YOLO version 3-voc2000 is not in the configuration folder. It's not in the data folder. Here it is in the main darknet folder. I'm going to copy the command that I just attempted to execute. Remove the CFG prefix from the path to our weights file, and to execute this command for forward propagation again. To display the image of the great blue heron, I execute the Python code image predictions.jpg. Here is the image of the great blue heron, with the heron identified as a bird, which is one of the classes of objects in the VOC 2007 and 2012 datasets. To use our darknet binary to forward propagate an image of a pin oak leaf from an individual of the species Quercus phellos, overlaid over a variegated background on my PC desktop, through a YOLO version 3 convolutional neural network trained on my own oak leaf dataset, I navigate to Google Drive's darknet folder, right-click within the window to all the folders and files in my darknet folder, left-click Upload Files, left-click Pin Oak Leaf, and left-click Open. I then navigate back to my Jupyter notebook and copy the image of the pin oak leaf from my Google Drive's darknet folder to the root content darknet data folder by executing the commands %cd ... copy from drive/my/escape character space drive/darknet/ pinoakleaf.jpg to darknet/data/pinoakleaf.jpg. I return to our root content darknet folder by executing the command $cd darknet. I then forward propagate the image of the pinoakleaf by executing the command !darknet, reference to the detector function, reference to the test command as opposed to the training command, reference to object.data, reference to YOLOv3-object.configure, reference to YOLOv3-object_2000.waits, and reference to our pinoakleaf image. To display the image of the pinoakleaf, I execute the Python code image predictions.jpg. And here is a very big but well-bounded image of the pinoakleaf over a variegated background, labeled with a bounding box and the class name Quarkus. To use our darknet binary to forward propagate video frames of a pinoakleaf translating and rotating in front of a variegated background on my PC desktop through a YOLO version 3 convolutional neural network trained on my own Oakleaf dataset, I cannot, to the best of my knowledge as of October 14th, 2019, copy a video from my desktop to my Google Drive's darknet folder, and then to the root darknet data directory. What seems like a workaround at this time is to enter the directory root content darknet data by executing the command $cd data, and to upload the video to this directory by doing the following. I execute the Python code from Google.Colab import files. Uploaded equals files.upload. Upon execution, I left-click the Choose Files button, left-click Pinoakleaf Translating and Rotating .mp4, and left-click Open. After waiting for the Python 3 kernel to upload some form of the video to the uploaded object, I execute the Python code for name and data in uploaded.items, with open name write binary as f.write data. This creates a version of the video into the root content darknet data directory. Then I return to the root content darknet directory by executing the command $cd ... From the root content darknet directory, I forward propagate the video frames of the pin oak leaf translating and rotating by executing the command /darknet detector demo function, demo command, a reference to object.data, a reference to YOLOv3-object configuration file, a reference to YOLOv3-object_2000.waits, the waits file, a reference to data pin oak leaf translating and rotating .mp4 in the root content darknet data directory. I specify the out file name parameter to be data pin oak leaf translating and rotating --label.mp4. And because of an error the forward propagation method throws, I have to append the flag don't show. It seems that frames of the video were successfully written. To view the resulting video, I navigate to the root content directory by executing the command %cd ... And I copy the video from the root content darknet data folder to my Google Drive's darknet folder by executing the command !copy from darknet data pin oak leaf translating and rotating labeled.mp4 to drive/my \escape character space drive/darknet/pin oak leaf translating and rotating --labeled.mp4. I then navigate to my Google Drive's darknet folder, refresh darknet, right-click within the window to all folders and files in my darknet folder, left-click download, and left-click save. I then right-click my File Explorer on the taskbar of my Windows 10 PC, left-click Desktop, and double left-click Pin Oak Leaf Translating and Rotating -- labeled.mp4. Excuse me while I transfer the resulting video from my other monitor. Here it is. In summary, I have provided you a guide in downloading darknet, Joseph Chet Redmond and AlexeyAB's deep learning framework, compiling darknet.solution into a darknet executable file, arranging data files, configuration files, weights files, and names files, executing commands to run the darknet binary and forward propagate an image through a YOLOv3 convolutional neural network specified by sets of those files, and drawing reliable, high-quality bounding boxes with object names around a dog, bicycle, truck, bird, and oak leaf. I have provided you a guide in executing commands to run the darknet binary and forward propagate input video frames through a YOLOv3 convolutional neural network, and drawing a reliable, high-quality bounding box with object name around an oak leaf being translated and rotated. Considering the limitations of the darknet deep learning framework based on my oak leaf training image dataset with respect to identifying oak leaves, it seems that darknet can successfully identify oak leaves varying color, shape, texture, size, background, lighting, and contrast. Darknet does seem to have problems, at least given my very small dataset and very few iterations of forward propagation of batches of training images, with small leaves, low resolution images, and images that are significantly yellowed due to low lighting. I believe that my first steps to resolving these problems are to expand my dataset, perform data augmentation and manipulation, and double the number of training iterations. Competing interests are expanding the number of leaf classes, which requires retraining from the base weights file darknet53.conv.74, and saving time, as training just my leaf detector took many hours on a Google virtual machine with a graphical processing unit, which was about 30 times faster than my Windows 10 PC in forward propagating video frames. All that being said, darknet is one of the fastest and most accurate deep learning frameworks for detecting objects in images, videos, and camera streams. Darknet is used in security, medicine, and the sciences. I am grateful to Simpson Weather Associates for offering me the flexibility to develop a proof of concept procedure for using Darknet to identify precursors to coal dust pollution from coal-carrying trains, and to efficiently and consistently identify proportions of coal dust in residential dust deposits based on microscope images of coal dust filters. In the near future, I hope to develop a procedure for using Darknet to label objects in a camera stream, to study the architecture of the Darknet deep learning framework, and to begin to conduct quantitative analyses of images, videos, and camera streams by accessing bounding box position and size, number of bounding boxes appearing over time, number of objects, and/or relationship of objects. I hope you enjoyed this guide and will find it useful and inspiring. I'm excited to hear what you could do with your procedure for using Darknet. I hope to create future videos presenting developing an image dataset, training a YOLOv3 convolutional neural network, forward propagating video frames in a camera stream through the network, and conducting data analyses. See you out there.